Hello all, in today's video we are going to learn about an error detection mechanism called cyclic redundancy check, CRC. Why is it named so? It is named a cyclic redundancy check because we are going to perform a check at the sender and as well as at the receiver side. Okay. Why are we using the term redundancy? I already told you redundancy is use of an extra information or extra binary bits for temporary purpose and later it is discarded. So here to provide error control, both in error detection and in error correction, we make use of some redundant or extra bits. So that is why we call it a cyclic redundancy check. So now let me tell you what is the basic idea of cyclic redundancy check and then I will show you the design. In cyclic redundancy check what we do is we have a data word that has to be sent. What is basically an error? Changing of bits from 1 to 0 or 0 to 1 is an error. So I have to find out whether an error has occurred. What is error detection? Finding out if an error has occurred. What mechanism I'm using? I am using CRC. So how do I do that? What I do is whatever data word I would like to send, to that I will add some extra redundant bits so that it becomes a code word, and that code word is being divided. I will make use of a division process here both at the sender side and the receiver side, where I will do division where the code word is divided by a divisor and I get a remainder. Now this remainder replaces the redundant bits that I have added and that is being given to the receiver. The receiver again divides the code word that it has received by the same divisor used by the sender and looks for a remainder. If the remainder is all zeros, it means that there was no error in transmission of data. If at all we get a remainder which is non-zero, it means that there was an error. So this is the basic principle on which the CRC mechanism works. So let me show you that we have a k-bit word that I have to transmit. To this k-bit, I am adding some redundant bits, redundant information to make it a n-bit word. This is called as a data word that I would like to transmit, and the n-bit word is a code word which I would like to transmit. So a k-bit word along with redundant information will become a n-bit code word. So how many redundant bits I am going to add? How many redundant bits are being added? The formula is n minus k. That means if n is, you have taken n as for example 7 bits and the k bits that you want to transfer are 4, then the redundant bits will be calculated as n minus k, which is equals to 7 minus 4, 3. So we will add 3 redundant bits to the information. So 3 redundant bits means what? I am going to add 3 zeros. What are we going to do? We are going to add 3 zeros to the right hand side of the data word. So adding 3 extra zeros to the right hand side of the data word will give you a code word. Now that code word at the sender side is divided. Divided with what? So the code word has become our dividend. What is the code word now? Code word is serving as our dividend, and now what we need a divisor. Now a divisor is called as a generator here. Why the divisor is called as a generator? Because the divisor is generated from a polynomial and the same divisor will be used by both sender and receiver because according to a protocol they agree upon the same divisor. Okay. Now what should be the size of the divisor? What is the size of the divisor? The size of the divisor will be with the formula n minus k plus 1. Okay. So now if I have a 7-bit code word, k-bit data word plus 1, that is 3 minus 4, 7 minus 4 plus 1, which will give me 4. So what is the size of the divisor? The size of the divisor is 4. Now let us see. I am telling division. So what division do I use? I do not use a decimal division. We are going to use the modulo 2 division. What division we are going to use? We are going to use modulo 2 division, in which we are going to perform the XOR operation. So now what we will learn is, we will learn about the generator polynomial. I told you that I am generating the divisor from a polynomial. How do I do that? What I do is, you can see here, I have for example x power 3 plus x plus 1 is given me has been given me as a polynomial from where I have to generate the divisor. So what I will do is I will see the coefficients of the terms in the polynomial. So you can see what is the coefficient of x power 3? It is 1. So I will take it as 1. Then if you see the x power 2 term is not specified. So the coefficient of x power 2, because x power 2 is not there, I will write it as a 0. Now you can see x power 1. What is the coefficient of x power 1? 1. So I will write a 1 bit here. Now you can see 1 is nothing but x power 0. X power 0 is 1. So what is the coefficient of x power 0? 1. So what is our divisor now? 1 0 1 1. As I told you, we are using a 4-bit divisor. Just now we have seen that if we have a 7-bit code word, 4-bit data word, we will have 7 minus 4 plus 1, which is equals to 4 bits of divisor. So this is how we generate a polynomial. This is how we generate a divisor from a polynomial. Now our divisor is ready, our dividend is ready. Now let us do the division. Okay, so how do we do the division? Let us see this process first. Let us see the flow of CRC. The flow of CRC is that what we do is, this is the data word that I would like to send. This is the data word that I would like to send. My data word is 4 bits. To this 4 bits, using the redundant bits, how many redundant bits I am adding? N minus k, that is 7 minus 4, that is 3 extra zeros I am appending to the right side of the data word. Now this data word with the redundant bits goes to a generator. What this generator does is, it will divide the code word with the divisor, and this divisor is the same divisor used by both the sender and the receiver. So now I have generated a data word along with 3 zeros. I will divide using this divisor, and whatever answer I get, that is my remainder, because the quotient is discarded here, only the remainder is seen. So the remainder 3 bits are added here. These 3 remainder bits replace the 3 zeros which we are adding here. Okay, the final remainder replaces the 3 zeros, and this code word is being sent through an unreliable transmission. Mark my point, unreliable transmission. What does it mean by this? It means that there is a possibility that the communication channel is prone to errors, and the 1 might change to 0 and a 0 might get changed to 1. So what happens at the receiver side? At the receiver side, just for understanding that we are at the receiver side, we have named the bits as B3, B2, B1, B0 and the remainder as Q2, Q1, Q0. Don't mistake it as quotient. We are discarding quotient completely. So the code word which has come from sender to the receiver, the same is being passed on to a checker circuit, where the checker circuit will again divide the code word it has received with the same divisor and gets a syndrome value. That this syndrome value is nothing but the remainder I am getting by the second division at the receiver side, and if this syndrome is passed to a decision logic which will check for all zeros. If the syndrome is all zeros, we will accept the data word and the syndrome is being discarded. This is redundant information. It is used temporarily, later it will be discarded. Okay, and then if at all the syndrome is non-zero, if it is 0, 1, 0, that means there is an error in the data, so we will discard the data word also. So this is the idea behind cyclic redundancy check. Now let us see an example here. This is the data word, a 4-bit data word I have to transmit. See an example. I have a 4-bit data word to be transmitted 1, 0, 0, 1. How many zeros I will add? My code word it has already told to me that n should be taken as 7. So what will I do? I will add 3 zeros to the right side of the message. Okay, so I have added 3 redundant 0 bits here. And then I will start division. How is the division? Modulo 2 division. What is the polynomial given to me? The polynomial given to me was x power x cube plus x plus 1. That will come to 1, 0, 1, 1. So I will take this divisor. I will take the data word along with the redundant bits as my dividend, and I will start dividing using modulo 2 division. So 1, 0, 1, 1 goes one time, as 1011. And which operation am I performing here? We generally do in division, we do subtraction, but here we are going to do XOR. This is the symbol for exclusive OR, where what is the truth table for exclusive OR? If it is alternating 1 and 0, the result is 1. If it is alternating 0 and 1, the result is 1. In case of same inputs, the result is 0. Okay, this is the truth table for exclusive OR. Now, when I say 1011 goes one time, I will write down it as 1011. I will perform the XOR operation. 1 is 0, 0 1 is 1, 0 0 is 0. Then I will take the next input. What is the next input? 0. Okay, but if you see, these 3 bits will not be enough. I need 4 bits. So what will I do? I will again write 0 times, 1011 0 times will give me 0. Then again I will do an XOR operation where I will get a 0, 0, 1, and then I will take the next 0. I have 4 bits. So now again 1011 one time gives me 1011. Again I do XOR operation. What do I get? I will get a 0 and 1 will be 1, 0 and 1 will be 1. I will take the next 0. Okay. Then again this bits will not be enough for me. So I will go for a 0 again. 1011 0 times. So I will take down this 0 here and again perform XOR operation. You can see I will get a 0, 1 and a 1. So this is my final remainder. I don't have any more bits left. So what will I do? I will get this final remainder 1, 1, 0. What I am going to do now is that I am going to replace this 3 zeros with the remainder which I got 1, 1, 0. Now this code word, if you can see, 1, 0, 0, 1 with the remainder 1, 1, 0 is my new code word which will be sent to the receiver. Okay. So now what does the receiver do? The receiver is going to again divide the code word which I have received. Now this is a code word I have received. Okay. The data word along with the redundant information. This will be divided by the divisor. Now this divisor, if you divide, you see again we do XOR division, 1011 with 1. You see that the code word has no change in the data that has been sent. Okay. So what we should get? We should get a non-zero, we should get a remainder which is all zeros. So you see, if I do one time, I will get 1011. Now I will do XOR division, that will give me 0, 1, and then I will take the next one here. Then I will do it 0 times, then I will get 101 and the next one I take down. Again I will do it 1 time, I will get 1011, then I will get all zeros. Okay, and again 0 times I will get 0. So what is the syndrome I got? The remainder I got is all zeros. That means there was no error during data transmission. But when we come to an error, for example, I am modifying this 1 bit during transmission to this 0, what will happen? If you divide, if you do this procedure, what you get is you will get a non-zero syndrome or a non-zero remainder. In this case, the data word is not being accepted, but whether it will be discarded. So, in what have we learned from this? We have learned that CRC is used for error detection. Okay, now let me tell you all that this is a lab exercise as well. You have to write down the code for implementing the CRC, where I'll just give you a pseudo code where you know what operations you have to implement in the program, in the lab experiment. You have to write the code for the XOR operation, because that is what majorly we are doing. Then you have to write down the code at the receiver side, where the receiver side will be checking and dividing the number, and you have to write the code for CRC, where what we do is we will divide the numbers by shifting the positions of the bits. Okay, so you need 3 codes here. You need a function for XOR, you need a function for receiver side, where the receiver side will be checking for all zeros remainder or all non-zero remainders, and the CRC where we actually do the division by shifting the bits and also calling the XOR operation. So this was about your error detection mechanism, CRC. Thank you.